So good evening. I'm Timosha, I'm the principal of the university. A great pleasure to welcome you to the University of Edinburgh Christmas Tamdale Prize Lecture. I'm very pleased to see future university professors as well as actual university professors, but very pleased to see that there's the wide range of participation here. The Tamdale Prize, and I'm delighted that Tam is with us tonight and that Kathleen is with us, has been awarded since 2008. It's to recognise the hard work and dedication of our academics in communicating difficult to understand science concepts to the wider community. And it's an annual prize which we have been now doing to really encourage science communication. And I think one of the great things in the University of Edinburgh is a real commitment to public understanding of science. Lots of key players, particularly Assistant Principal Professor Dorothy Crawford, has really helped us enormously with that mission and with this prize. The prize was named after Tam because, as well as having served as our rector, much more importantly in this context, for 36 years he wrote a weekly column for the New Scientist. And when he retired from his column in 2005, normally the New Scientist just passes over retiring columnist, but it made an exception, and it marked his retirement with an article. And here's an extract. The best columnists do not merely present opinions, they provoke, educate, pursue the truth, and challenge authority and orthodoxy. And by those standards, Tamdale, whose final Westminster Diary appears this week, has done an exemplary job in the and Tam, obviously, is very well known, you know, for being in the awkward squad politically, but he's also been tremendously good in the challenging squad scientifically, and that's a very helpful role to have played, done with great distinction. And Tam provided a conduit for researchers to speak to Parliament and vice versa, and he wrote about everything from dam safety to the plight of war veterans and the availability of anti-venom. And he covered all manner of environmental issues, nuclear power and chemical weapons. And he displayed the same doggedness in preparing his column as he did in the House. So with tremendous contribution to scientific understanding that Tam made there. So the prize, which Tam will give later, goes this year to Professor Colin Pulham. And it's very appropriate that we've got a chemist because 2011 is the International Year of Chemistry as designated by UNESCO. And Professor Pulham leads an active research program in the field of high pressure chemistry, and he's got an international reputation in that area. And since November 2008, he's been the Director of Teaching in the School of Chemistry, with responsibility for ensuring that the school continues to deliver excellent and even more excellent teaching. He's also for the last 16 years, played a major role in the School of Chemistry's public engagement program. He's done lots and lots of things, and he's been recognised externally by two of the most important awards that he could get. The first was the Royal Society of Chemistry Royal Institution Prize for bringing science to the public, and that was presented by Her Majesty the Queen in 1999. And the second was the Royal Society Cone Award for Excellence, engaging the public with science in recognition of his achievements for engagement with society in matters of science, awarded in 2005. So now it's a tremendous pleasure to ask him to speak to the topic, Chemistry, Our Life, Our Future.
Thank you, Principal, and thank you all very much for coming up on this cold night to this demonstration lecture. I've chosen the title, which is Chemistry, Our Life, Our Future, because that's the title for the International Year of Chemistry. And what I'm going to show you, hopefully, is how chemistry improves our life and how we can hope that chemistry is going to continue to improve the quality of people's lives. So I need to make some thank yous, and I'd particularly like to thank a number of people, including these four people who have been science communicators who have worked for us over the years. Some of them actually I noticed who are in the audience, and some of them will actually probably recognize some of their slides. So I shall also highlight that. The people highlighted in red, Dr. Jenny Rogers, Dr. Elizabeth Stevenson, and Professor Leslie Yellowlees, I owe a particular debt of gratitude to because they've been working with me for a number of years. And I'd particularly like to thank Professor Leslie Yellowlees, who got me into this. One day, back in 1994, I think it was, she said, come down to the Science Festival, take part in this demonstration. I went down not knowing what to expect. I watched one of the lectures, and then she said, right, it's your turn now. And I remember getting up and doing that and getting this real buzz for about 10 minutes or so, and I thought, yes, I'm hooked on this. And I see that same reaction when I see it in the junior researchers, younger researchers who we expose to this sort of activity. I'd also like to pay tribute to Paul Atfield and Dr. Neil Robertson, who've also been very, very supportive. Paul Atfield is the director of the Extreme Condition Centre where I work, and Dr. Neil Robertson is provided a lot of the impetus on some of the solar cell work, and I'll talk about that a little bit later. So the question is, where does public engagement fit into academic life? Well, I firmly believe that this really is a three-pronged triangle. I think teaching and research is a well-known synergy, but I think also public engagement also ties into teaching. So I use some of the demonstrations that I'm going to show you today in my lectures, and I think that helps to engage the students. I think it's also being able to communicate to a variety of audiences helps your research. That may be communicating with other academics. It may be communicating with industry, where you may be talking to people well outside of your discipline. So I think this really is truly a virtuous triangle, and I would urge colleagues to consider this themselves. Just to very briefly tell you what the objectives of the International Year of Chemistry are. So it's about increasing public appreciation and understanding of chemistry and how it meets world needs, and I hope I can show you that. It's about encouraging the interest of young people in chemistry, and I see some young people in the audience, so hopefully I can inspire you today as well. It's about the future and how chemistry is creative. I really do believe it's a creative subject. And very importantly, it's about celebrating the role of women in chemistry, and it's particularly celebrating the Nobel Prize of Madame Curie. So that's what we're here today. I hope I can meet some of these objectives in today's lecture. However, I'm passionate about chemistry, but that is not necessarily what the media and perhaps the wider public's view of chemistry. And here we see a chemical pollution. It's very topical in the news is the Bhopal disaster, where the repercussions of that, where many thousands of people died in a big chemical incident. And really, I think this really was a black spot in chemistry. And so, perhaps justifiably, chemistry does have a poor reputation. I hope I can convince you otherwise. And the first thing I'm going to show you is the chemistry in the ozone hole. So this was discovered by chemists, careful measurements of the ozone concentration over the poles. Chemists realized that actually the ozone hole was becoming depleted. And then they did some superb work on actually trying to understand what was causing the problems. And one of the culprits was this compound, which is an example of a CFC. It reacts with ultraviolet light, and it produces chlorine atoms. These chlorine atoms then react with ozone. And the trouble is, this is a catalytic reaction, and so what we end up with is one chlorine atom destroys many millions of ozone molecules, resulting in this decrease in the ozone concentration. So chemists identified this with careful measurements. They convinced governments, and governments took steps, and we now have banned these harmful CFCs. So I want to move now to a little bit about, I'm going to just start doing some demonstrations, so I'm going to remove my jacket and switch over to the white coat. And we're going to do some chemistry here. And what I'm going to illustrate is how we detect metals, which may be in the environment, or perhaps would be in somebody in the blood. And what we're going to do is to use the sort of techniques used by chemists. So the first thing I'm going to do is to put on some safety glasses. And I'm going to pour some methanol, which is a flammable liquid, and we're going to have a little fire, first fire of the day. And we're going to see how this methanol burns like. If I get my matches, my matches to burn. we go. Now, you may not be able to see very much there. It's a very, very pale flame. It burns with a very, very blue flame. And I've deliberately chosen methanol because of that very reason. And what I want to do is to introduce into that flame some copper. I've got some copper chloride solution here, and I'm going to put that into the flame, and hopefully you can see the colour changes. A lovely green colour there, characteristic of copper. Let's try something else. I've got another compound here, which is lithium. Anybody like to guess what colour lithium is going to be if you're a non-chemist? Any ideas? Yellow? No. Let's see what it does. Hopefully you can see that's a beautiful, beautiful red colour. Very, very beautiful red. I've got another red colour. I think it's a particularly important one. This is a salt of strontium, which was actually discovered in Scotland in the place called Strontium. Now that doesn't look right, does it? It should be red. Oh dear. That's supposed to be a lovely red colour, but I think that's been contaminated. So let's move on that one. And this actually illustrates quite nicely the worries about contamination. So is this really? Of course, it was all deliberate. Is this really? Let's try something else, which I know is fresh out of the bottle today. So no doubt about this one. This is potassium. Any guesses on potassium? Purple, very good. So we have a lovely purple there. Does it show up on the camera? Yes, I think it does. Yes, so we've got a lovely colour there. Got some interesting reactions going on in the methanol there. It looks a bit distinctly messy. And I've saved the most intense colour for last, and that's sodium. And everybody, I hope, should get sodium because this is what you see in street lamps. And so we should see this lovely, very, very intense yellow flame of sodium. So we can therefore identify what particular metal ions are there, either as solids or else perhaps in solution. And this is going to be important if you're going to identify effluent from mines, perhaps, taking samples of blood, and understanding what is actually in the system. Just what's the chemistry going on there? Well, we've got a little slide here which shows that. So what we're doing is we're applying heat to these atoms. We're turning them into the excited state, and then they drop back down in energy, and they give out the light. So that's the process which is taking place. And we have this very distinct energy gap, which is this gap here. And if we change the metal, we get a different color, different energy gap, and therefore a different colored light. So this was our lithium, and this was our copper, and you can see we can very easily distinguish between the two. So a very good technique for analysis. So I think it's fair to say now we have a much better understanding of how chemicals interact with the environment. There is now an awareness of that. Chemistry, I think, plays a crucial role in environmental monitoring, and we can monitor the atmosphere, groundwater. We have a legacy of contaminated land, and chemistry can help us understand how you remediate contaminated land. We're interested in minimization of waste, more efficient routes to chemical compounds. And if you have your waste, how do you treat it, and how do you treat it safely? Now, this is a very, very important slide. This is chemistry and climate change. And I just want to highlight, I'm sure many of you have seen this before, this is the concentration of carbon dioxide over the last 140 years or so. It's going up, and it's going up increasingly steeply. And I'm sure you'll be already well aware of the possible consequences of this continuing rise in CO2. We have increased temperatures, potentially through the greenhouse effect, global warming, and we really have to be very, very careful about what's going to happen in future. So what are the consequences of this? Well, we have rising sea levels, and so this island disappears. We have shrinking ice caps. We have severe weather. We have tropical storms. Or we have drought, famine, and multiple deaths. So it really is of global importance, of global significance. But that's what happens to the carbon dioxide in the atmosphere. But we must not forget that we have a large volume of water. This is in our seas and our oceans. What happens to the carbon dioxide in these systems? So what I'm going to do then, first of all, is to have a look at what happens to carbon dioxide when we add it to water. I've got some good Edinburgh water here from the George Square Lecture Theatre, and I'm going to test it to see whether it's the correct pH. It should be pH 7, which is a nice green colour. Yes, that looks good. Does it still look green on that? Maybe that nice and green. So that's probably drinkable. Let's put some sulfuric acid in that and see what happens to it. So I'm going to stir that round and we'll see what happens. And hopefully we should start to see a colour change. Yes, that's looking good. Nice red colour there. So acid will turn it red. Opposite of an acid is a base. So I've got some concentrated sodium hydroxide solution here. So just a few drops of that should do the job. We should go back to, hopefully, to green a bit more. That must have been stronger acid than I thought. Still no change. This is very much like a first-year experiment, saying, where's the end point? Where's the end point, Professor Pulham? Well, eventually we're going to get there. We'll just be brutal, shall we? There we go. So overshot, and we've got ourselves a lovely purple colour, which is our alkaline. So that's the scale. That's the pH scale. This universal indicator is our dye, our indicator. And what we're going to do now is to put in some dry ice. So this is carbon dioxide. It's at minus 78 degrees Celsius. It has the interesting property that it turns directly from a solid to a gas. This process is called sublimation. So there is no liquid form, no liquid state. So we throw that in. And hopefully now you can see not only do we get our beautiful lots and lots of foam, lots of steam, but we also get a colour change. So it's gone through to yellow, and we leave that long enough, that should eventually go through to red. And so that immediately tells you then that carbon dioxide is an acidic gas once we dissolve it in water. We can also, of course, tell, look at the properties of this carbon dioxide is heavier than air because it's sinking. So how does that affect what happens to our oceans? So this is what we've done. We went to increasingly acidic. That was the basic scale. Why does this happen? We have this equilibrium. So what is happening is we have carbon dioxide dissolving in water to form this material here, which is called carbonic acid. It's the same stuff which is in fizzy drinks. And this is slightly acidic. This dissociates, and we get this H+, and that's the origin of the acidity. So what happens to the ocean ecosystems? Well, coral reefs are particularly susceptible to changes in acidity. And because they have so much interdependence, on there, they end up having major effects on a whole variety of different other life forms, which are dependent upon the coral reefs. So we have to worry then about what happens to our carbon dioxide, not only when it goes into the atmosphere, but also when it enters the sea. So what do we do with our carbon dioxide? Well, in principle, we can store it. But we've got to store it at temperatures below minus 78 degrees C if we want to store it as a solid. So that's not particularly easy to do. One possibility, and this is very current in the news, is to pump carbon dioxide at high pressure in liquid form deep beneath the sea and put it into these empty oil field reservoirs and hopefully store it there until we can think of something more useful to do with it. But there are serious issues with that. Not only is it very expensive, but we also have to worry about the chemistry of this carbon dioxide dissolved in brine, what it does to the rocks, what does it do over a long period of time. And that's a bit of research is still underway, actually up the road at King's Buildings in the geosciences and chemistry departments. Now I want to tell you a little bit about chemistry and energy. These are all familiar appliances. They all require energy, and energy is one of the challenges, I think, that we as the 21st century, we have to be thinking about how are we going to generate our energy. Where does most of our energy come from? Well, of course, it comes from oil, it comes from gas, it comes from coal, and we burn it in power stations and generate our electricity in this way. And just here's an example of combustion of methane gas. So this is the reaction. Methane and oxygen gives us carbon dioxide, water, and energy. And immediately you can see some of the issues associated with burning fossil fuels. Not least is the production of carbon dioxide and this potential to be a greenhouse gas. I think also limited supplies of coal, oil, and gas are also a current issue. As a chemist, though, I get very disturbed when we burn these very valuable feedstocks, particularly oil. Oil is very rich in a whole different range of different chemicals, and it would be far better perhaps to use the raw ingredients from oil to make plastics or other useful materials rather than actually to burn it. So these are some of the problems then we have with burning hydrocarbons. So the obvious question is, can we use fuels that actually do not produce carbon dioxide? And of course, one that perhaps everybody may be familiar with is hydrogen. And hydrogen has lots of attractions because if we burn hydrogen in oxygen, we get water or steam, and we get energy. Just how much energy we do get out of that, I can demonstrate in the following reaction. What I'm going to do is I've got a Coke bottle here which contains a mixture of hydrogen and oxygen. Notice that it hasn't exploded. It's a very stable mixture at the moment. And one of the reasons it's a very stable mixture is because there's a relatively strong hydrogen-hydrogen bond. However, if I break that hydrogen-hydrogen bond, and I could do that with matches, but that's an easy way to do it. I'm going to do it in a more interesting way, and I'm going to use a catalyst. And the catalyst I'm going to use is palladium dispersed onto some activated carbon. So it's a black powder. I don't need very much of it. Now if this works, this should be very loud. So you may want to protect your ears. So there's a little bit of palladium on carbon. This is a 50-50 mixture. I'm going to take off the top. I'm going to drop it in and then walk away. And there I hope you saw and heard and felt the hydrogen-oxygen mixture. The bottle's slightly warm, a little bit of steam coming out of there. So there we've made ourselves lots of light, heat, and a lot of sound. So that's all very well. We can certainly burn hydrogen, and we could burn it in an internal combustion engine. What we really want to be doing, though, is to taking that hydrogen and turning it directly into electric power. Oops, that's the wrong one. And we want to turn that directly into electric power. Some of you may have noticed that there was a little delay there. It was about two seconds delay, which gave me enough time to walk away. So we need to explain what happened there. We have our strong hydrogen-hydrogen bond, which is what I was talking about here. But we have this palladium surface, and the hydrogen has a very strong affinity for palladium, and it starts to bond. And what happens is this hydrogen-hydrogen bond gets weaker. Eventually it gets so weak that it disappears, and essentially what we have here are hydrogen atoms on that palladium surface. And that process takes a little bit of time, and that was the time it took, the 2 or 3 seconds for me to walk away. These hydrogen atoms then are much more reactive. They react with the oxygen, we get this chain reaction, and we get this explosion. So that's if we want explosions. As I mentioned, though, earlier, we want to have smooth generation with no sound, no bangs, no uncontrollable reactions. So what we do is therefore use is the idea of a fuel cell, where we mix hydrogen and oxygen through a catalyst, through a membrane. We may generate water and our electrical energy. And these fuel cells are operational, and you can even drive hydrogen-powered cars on using these types of fuel cell. The question is, of course, why do we not routinely drive these hydrogen-powered cars? Why are we still obsessed with our internal combustion engines? Why are we still filling up with petrol and diesel? Well, one reason is public perception of risk. If you mention hydrogen to somebody, they may think, they'll have this sort of image perhaps in their mind. This was the Hindenburg in 1937. It was a German airship flown over to the US, and there was a fire, and what we saw there is the hydrogen burning. Notice that the hydrogen is burning upwards, but we also saw burning of the fabric here. And in fact, although the hydrogen did burn, it was actually the fabric which caused most of the casualties, because it was the fabric which actually fell on top of the passengers and caused the deaths. So we have an issue here then in terms of explaining to the public how safe are our fuels. And hydrogen has perhaps an unwarranted nasty reputation. But the other question we've got to ask ourselves is, where does this hydrogen come from? It doesn't exist naturally on the Earth. It's lighter than air. It escapes into space. So how do we currently generate hydrogen? Well, we actually generate it from methane and other hydrocarbons in these types of reactions. So we're using a fossil fuel, and we're generating a greenhouse gas. Right? So we're actually not making things any better for ourselves. And therefore, one of the things that we have to do is to think about what's the origin of our fuel. So how can we make hydrogen? Well, we can do this in another way. We can do the reaction between certain metals, water or steam. So let's see if we can do that. And I'm going to use a metal which is very common, and of course is aluminium foil, aluminium cooking foil. And of course we routinely regard this as being a relatively inert material. We typically put it in the oven at 220 degrees Celsius. Think no more about aluminium as a relatively unreactive material, until we actually scrape away this protective oxide layer. And what I'm going to do is remove that oxide layer with some concentrated sodium hydroxide solution. If we add a little bit of that, again, there should be a little bit of a delay. Whether you can see any reaction there yet. It's a little bit of bubbling. The aluminium foil is starting to move. So what happens is the oxide layer is destroyed by the sodium hydroxide. That exposes the fresh aluminium, and then suddenly we get gas being produced. Let's see what that gas actually is. And it is clearly hydrogen. And if we're lucky, we may even be able to get it to burn the mouth of the tube there. You see the characteristic flame there. And you really can see this is a really quite vigorous reaction. These poor bits of aluminium are being chewed up by the sodium hydroxide solution, which is a very good reason why you shouldn't use sodium hydroxide-based cleaners on aluminium kitchen utensils or aluminium surfaces, because you'll certainly discolor the aluminium, and you may even have enough reaction to get some hydrogen gas given off in this way. Hopefully not as violently as this. So that's one way of making hydrogen. Another way, of course, is to electrolysis of water. So if we split water, passing electric current through it, we get 2 moles of hydrogen and 1 mole of oxygen. But of course, in order to do that, we've got to have a clean source of electrical energy. And so renewable energy based on wind and water is currently a very topical aspect. And so we can do that from hydroelectric, we can do it through wind power, we can do it through tidal, or we can do it through wave power. So this is a possible way then of generating your hydrogen. It doesn't actually solve some of the other problems of how to store it. Hydrogen is a gas, as we've seen. You have to store it either at very low temperatures, which requires energy, or very high pressures, which also requires energy. And so people are looking at clever ways of storing hydrogen in solid form, either in a large combined in a metal hydride, or perhaps absorbed onto certain materials such as metal organic frameworks. We can also turn to biofuels, here where the energy of the sun is captured, for example, by plants, turned into carbohydrates or oils. And we can then ferment those carbohydrates to give us alcohol, which we can drink in the form of vodka, or perhaps more usefully, add to gasoline or petrol and run our cars on a mixture of alcohol-doped gasoline. This is not without its problems, of course, because many parts of the world are still starving, and so there is a big ethical dilemma here. Should we actually be growing crops for fuel when we really perhaps should be growing them for food? And I think that's a very serious debate that we have to have, and has all sorts of implications for the price of wheat, grain, and other materials. We can also, of course, generate electricity from sunlight. So this is my recently installed solar panels on my house. I've got just under 4 kilowatts of generating capacity. So this is a nice sunny day in August, and everything was going really, really well, of course. Didn't do quite so well in recently when the very short days up in Scotland, where perhaps my generation totals are much less. If you live in a really sunny place, then you could even power your little car in this way. But even solar power is not without its problems. And because one of the first questions we've got to ask is where does the silicon, which is used in these solar panels, where does it actually come from? Well, one place it comes from is the beach. It comes from sand. And there's this little chemical equation here where we take silicon dioxide and sand, carbon. Look at the very high temperatures we have to use. So this is going to be an energy-intensive process. And look, we also generate carbon dioxide. And so my solar panels there, although they're producing energy, it's actually going to take them about 5 or 6 years before they've actually overcome the amount of carbon dioxide that they've actually been used in their production. So that's also an issue. And this is also one of the reasons why solar panels are also, silicon-based solar panels are also so expensive. It requires a lot of energy in order to get the high-quality silicon panels. So this has prompted a number of research groups, not least my colleagues, Dr. Neil Robertson up at King's Buildings, to look at other types of solar cells. And one particularly promising idea is this idea of something called a dye-sensitized solar cell. They're quite complex systems, but the important features of them is that they, instead of using expensive silicon, they use cheap oxide semiconductors, something called titanium dioxide, which you can actually dig out of the ground. They use polymers, and they use these dye molecules. So the idea behind these is that these are potentially low cost, they're lighter weight, they're flexible, and so you could roll out a screen wherever you needed it, rather than having these rigid panels that I've got on my roof. Non-toxic, hopefully, and easy to manufacture. So this, I think, may well be the future of solar cells if colleagues are able to carry on the developments that they've got. I would recommend this website to anybody who's interested in solar power. And this is, again, my colleague, Dr. Neil Robertson. This is the Solar Spark. It tells you some experiments that you can do investigating solar power, tells you what's new in the solar energy systems, and it tells you what new developments have been going on in the research side. So just to summarize the energy problem, we need access to safe, clean, sustainable energy is clearly one of the big challenges for the 21st century. I firmly believe that chemistry will provide the solutions. Our creativity of colleagues will undoubtedly triumph. Now I want to change gear a little bit now. I want to talk a little bit about chemistry and catalysis. So catalysis is the fancy name for speeding up a chemical reaction. And a good example of this is this very important reaction, ammonia. Synthesis of ammonia, which comes from nitrogen and hydrogen. Large amounts of ammonia are made in this way. Ammonia is vitally important as a fertilizer. This reaction is really rather slow unless we use the correct sort of conditions, and catalysts are absolutely crucial for that. So what does that mean? Well, these are our starting materials here. These are our products. So the reaction is ultimately downhill, but we have to go over this barrier, and we call this barrier a transition state. And you can see this is actually quite a large barrier. If the purpose of a catalyst is to lower this barrier, and so instead of the barrier being the height B, it's now the height A. If the barrier is smaller, then we can have a faster chemical reaction, and we can generate ammonia, for example, much more quickly. Many other compounds are made using catalysis, so plastics and polymers are good examples, things like polythene. Nitric acid, again, a major chemical feedstock, also used in the fertilizer industry. And of course, pharmaceuticals for healthcare rely very heavily on catalytic processes. So I want to show you a little bit about, demonstrate some catalyst. And I'm going to use hydrogen peroxide as an example. Now, Marilyn Monroe was a great fan of hydrogen peroxide. She used it extensively on her hair to give her that peroxide blonde. I used to use it as a young man, and look what it did to me. This bombardier beetle also uses hydrogen peroxide. It uses it as a means of protecting itself from predators. When under threat, it has a reservoir of hydrogen peroxide in its body. It passes it over a catalyst, and this catalyst results in a chemical reaction where hydrogen peroxide is decomposed to steam and to oxygen. So this is what's coming out here is a hot jet of hot water with some hydrogen peroxide in there. A very unpleasant mix, and that deters the predator from gobbling up the beetle. So let's do that. Let's do that reaction, shall we? Let's see if we can recreate our bombardier beetle. So I have in this measuring cylinder a catalyst. The catalyst is actually a potassium iodide solution, and I've got some soap in there. I've got some very strong hydrogen peroxide, which I'm going to pour in there, and hopefully you'll be able to see a catalytic reaction. Look out for color changes. Look out for changes in form. Let's see how this goes. And there we've got our own version of the bombardier beetle. You may be able to see some steam coming out off there. And so what's happening here is we've decomposed our hydrogen peroxide. This foam is actually bubbles of oxygen, and we've got a fair bit of heat there. That's about 40 or 50 degrees Celsius coming out of there. So that's a catalytic reaction. The hydrogen peroxide will sit quite happily in this bottle, slowly decomposing over time. It needs this catalytic reaction in order for it to decompose more rapidly. So, chemistry and health. Chemistry has produced an enormous contribution, I think, to people's health. We have analgesics, painkillers. We have antibiotics, which destroy bacteria. Antiseptics, which keep ourselves clean. This very important drug, cisplatin, one of the most successful anti-cancer drugs that's ever been on the market, is a very, very potent drug. And more recently, these antivirals for defeating things like bird flu and other types of viral infections. And there's a fascinating history, I think, for chemistry and health and the design of medicines. So one of the first materials that was used, came from, was extracting willow. Our ancestors knew that willow was a rather useful material for reducing inflammation and fever. And so some German chemists back in the 1800s identified salicylic acid and extracted salicylic acid and found that this also had, this was the active ingredient in there which was responsible for reducing fever. The trouble is salicylic acid is actually a very corrosive material. It's actually used to treat warts on the skin. So if you actually ingest it, it's not particularly good for the stomach. And so what they realized was that the reason it was very, very acidic was this OH group here. And what they did was they did a chemical reaction called acetylation. So they replaced this OH with this functional group here to produce something called acetyl salicylic acid, aspirin. Aspirin, of course, has been widely used as a fever-reducing treatment, and more recently has been used, of course, in treatment for strokes victims and also heart attack victims, where it operates by thinning the blood and preventing further attacks of heart attacks or strokes. Related to aspirin, is a relatively new painkiller called 4-isobutyl alpha methylphenol acetic acid. It's a bit of a mouthful when you go to the chemist, so more usually to say ibuprofen. And this is a purely synthetic drug. But what you may notice, of course, is that there are some similarities. So we've got this ring here. This is this ring of carbon atoms. We've got this carboxylic acid group, which is also replicated in our aspirin. And so what the chemists are able to do then is to really to be able to fine-tune these molecules. They can build and design molecules pretty much however you want. I wanted just to say a bit about, this is about plant health, and this is a very topical, a very example here. This is called azoxystrobin. It's quite a complicated molecule. It was first discovered, or some of the first derivatives were discovered actually in Czech forests. They found that actually there was a fungus which was producing this, and there was no other fungus being produced anywhere near the fungus that was growing. So clearly this fungus was protecting itself from other fungus by secreting something. So these derivatives were isolated. They were found actually to be too light sensitive to be useful, and so then chemists at ICI or Syngenta down the road at Grangemouth modified and developed this material, and this was the final product that was developed. It's widely used, very, very powerful antifungal agent. It's incredibly important for wheat crops, rice crops, and really a whole load of foodstuffs which are susceptible to attack by fungus. So this is a good example there of where chemists have learned from nature, modified natural materials to produce compounds which are particularly valuable and sustain our food supply and keep us with food security. Chemists are also very good at protecting us from harm. So water purifying tablets are perhaps one of the most, made a major contribution perhaps in health, particularly in third world countries, where access to clean drinking water is absolutely crucial. These water purifying tablets are able to destroy bacteria and make water drinkable. If you go out into the sun, we have to protect ourselves from the harmful ultraviolet radiation, and so we need to protect ourselves with things like titanium dioxide powder, and this is usually incorporated into some sort of sunblock and prevents us getting cancer. About 8 years ago, I managed to fall off one of my colleagues' boats down at Port Edgar and ended up with a broken elbow, broken arm. And this is the metal plate which is in there and actually is still in there. And without this, my elbow, I think, would have been unable to ever to move my elbow again. This was a particular type of steel alloy, relatively lightweight, but most importantly, resistant to attack by the body. So it's been in there for 8 years. It only aches a little bit when it rains, but otherwise it's no real issues. And I should probably keep it for the rest of my life. When I'm getting a little bit older, perhaps my hips might start to go, and I will need a replacement hip. Again, lightweight alloys are absolutely crucial. I mean, this is a relatively big piece of metal, and you really don't want to weigh the patient down with an enormous weight here. And so it's very important, though, to have on top of this metal, which is inserted into the bone, you need to have something which is going to be biocompatible, i.e. the body doesn't recognize or doesn't realize that it's a foreign body and start to attack it. So chemical coatings for biocompatibility are absolutely crucial. So chemistry and materials, and perhaps the early materials chemists, I like to tease my materials chemistry colleagues like this, that they're alchemists. They were trying to turn lead into gold. And even in these early days, you can see the economic driving forces for chemistry to create wealth. So let's see if we can actually do that. We're going to go for copper into silver or gold, and I'm going to demonstrate that in this little setup. So I'm going to set up my burner, and I'm going to put in there some concentrated sodium hydroxide solution, which we could perhaps regard as the alchemist's water. I've got some zinc, or alchemist's earth, and I'm going to throw that into the mix. This is zinc dust. And I've got, I hope the camera can pick this up, 2 shiny copper coins. Right, they're definitely copper, 1-penny pieces, and we're going to stir those up. We're going to say a few alchemist spells, and hopefully we're going to see a chemical transformation. It looks like it's happening. I'm getting a chemical reaction. What I'll do is just to be safe, I shall take that off the boil, manipulate that, and then I've now got a coin here which is looking a little bit silvery, which is looking good, but I'm just going to clean off the excess zinc, and then hopefully I can show you the results of my handiwork. And there, I hope you can see, we've now got, if you can zoom in on that, you can see that we have made indeed a silver coin. But of course, silver's not enough, so let's see if we can do this a little bit. Let's go for gold, and I'm going to heat this in the flame. And with a bit of luck, you may start to see some changes. Okay, has it changed? Yep, that's looking pretty golden to me. We'll just cool that down. There we go. And we've now got ourselves a beautiful, can we zoom in on that? A lovely gold 1-penny piece. So which you can, perhaps somebody like to catch this? Would you like to catch this? Oh dear. Or you can perhaps get that at the end. So, of course, there are issues associated with this. Not least, it's about defacing the coins of the realm, which is actually a criminal offence. And so the last time I met Her Majesty, I politely asked her whether she wouldn't mind if we carried on doing this demonstration, and she agreed. So we clearly, I don't think I would be here if I was really able to turn copper into silver or gold. We know now as chemists that you can't do that except under very specialized circumstances in nuclear reactors. So what we're actually doing there, of course, is coating our copper coin with zinc. And then the zinc is then being alloyed when we heat it in the flame with the copper, and we get the gold-colored brass. So these are all surface effects and good examples of materials chemistry. I want to say now a little bit about structure and properties, and I want to illustrate this with graphite and diamond. So graphite you're very familiar with. It's in pencils. It's very, very soft. We can have, it's electrically conducting, we can write with it. And if we look at the structure, we can understand perhaps why graphite is so good as a pencil, because these sheets rapidly will slew off, and we can put our graphite onto the paper. If we try writing with diamond, on the other hand, which is very, very hard, electrically insulating, and of course very, very shiny and much more valuable, then we can run into real problems. And of course, this is the same element. Both of these contain carbon. It's just simply that diamond, the carbon is joined to 4 other carbon atoms in this infinite lattice. It's a very, very strong material, very, very hard, and we can have very, very different properties. One of the things that we're able to do up at the King's Buildings Centre is to take graphite at very high pressures and temperatures, and in principle convert it into diamond. The trouble is the yields are very low and the energy costs are so high that this really isn't worthwhile on a sort of scale that we're working on. But it is, of course, an important application for making industrial diamonds on a very large scale. Now I want to tell you a little bit about structure and colour, and what I want to illustrate this with is a compound called Cobalt Chloride. which gives you a very pale coloured solution. It's a very pale pink, and I've painted something on here which you probably can't read at the moment, hopefully, until I turn my heat gun on this. And I hope you can start to see some of the letters appearing there. Hopefully that says IYC, International Year of Chemistry. And what we've done there, created, of course, then is a form of invisible ink, which only becomes developed once you expose it to heat. So we should just explain what the chemistry is going on, and that's shown in this slide here. What we have then is our cobalt chloride, and it contains, in solution, it's this pale pink colour, and it's got 6 water molecules around it. That's what was on the paper, and was this very, very pale colour. If I heat it, that water is driven off, and we get instead this time a cobalt surrounded by 6 chlorine atoms. And this is the blue colour that we've got there. It's great for invisible ink. It's very good if you're a secret agent, like Agent Jenny Rogers, who's in Moscow there. This was how she communicated back home when she was at the Moscow Science Festival. So I'm emphasizing the importance of structure. And how do we determine structure? Well, we can do some of that in the laboratory, but one of the things that I do is make extensive use of large-scale facilities. And I use something called the Diamond Light Source, which is an enormous facility based in Oxfordshire. You can just see the scale here. You could actually drive a jumbo jet around this ring internally with room to spare. What we have is a series of it's this ring. We have fire electrons around this ring at very, very high speeds, and then you see these magnets here. We apply magnetic fields to these, and we get very, very strong, intense beams of X-rays, which we can focus on our samples, and that tells us about the structure. So that's the Diamond Light Source. And right next door to the Diamond Light Source is the ISIS Neutron facility, which is this bit here. This is a neutron factory, if you like. It's very large scale, lots of big bits of equipment. And again, we generate neutrons, again, to look at the structures of materials. And this is the way, so instead of making neutrons in a nuclear reactor, we do this using what's called a spallation source, where we fire very charged particles, protons, at a tantalum target, and we end up with a beam of neutrons being fired out. So these are our protons. They hit the target, and then they get fired out. We get our neutrons, which we then use to interrogate our structures. So that's where I do a lot of my research. And it's all very well having these great facilities, but you've got to have dedicated people who are prepared to work all night and put large amounts of time and effort. And these are the sort of the young researchers who take part in these sorts of experiments. You can see them deep in thought, and also clearly somebody who's had too late a night and probably really ought to be going to bed. One of my area of research is actually looking at energetic materials, which is the polite name for explosives and propellants. And this is what I'm doing. What I've been doing here is loading a sample of a compound called RDX, which is used in plastic explosives, and we're squeezing it to 39,000 atmospheres at one of these central facilities. And what we find is that the molecular shape changes and the crystal structure changes, and from that we're able to understand better how these materials behave when they detonate at these very, very high pressures. And one of the drivers for this is actually to understand the factors which make explosives more safe, less likely to undergo accidental initiation. It doesn't always work out that way, so sometimes things go bad, so go wrong. So this is where we had a failure of our anvils. The anvils came together, caused a little detonation of about 100 milligrams of material and caused this sort of damage. I should assure you that no postdocs or postgraduate students were injured or harmed in this experiment. All this is done in a contained environment. So materials for entertainment and safety. Well, we can't really avoid having the fireworks of the tattoo. We've got our materials here for signalling on a cold Scottish mountain, and of course our Christmas crackers. On a more sort of serious note, of course, is the importance of airbags. I just wanted to show you this little video, which illustrates quite nicely the speed with which airbags actually inflate. So this lady wants to cross the road. So there you see the very rapid inflation of the airbag, large amounts of gas generated very quickly, which prevent you going through the windscreen. You might want to stand back a little bit for this one. And then we also have the triumph of age over wealth, where the lady clearly wins. So I've got some material here which has been slowly drying out. This is called nitrogen triiodide. Some of the older members of the audience might remember playing with this at school or at university. It should now have dried out sufficiently to be sufficiently friction sensitive. So if I tap it gently, it should go off with a bang. So this might be quite loud, so you may want to cover your ears. Sometimes it all goes off at once, which means it will be very loud. So let's just try it on this sample here. And indeed, it has all gone off all at once. And you can see we've managed to blow a hole through our thing. I think the table is just about intact. And some of you may notice the lovely purple cloud which is wafting through the air. It's very, very good for clearing up colds. But of course that's iodine vapor. And what we're seeing there is a very rapid reaction between a decomposition of nitrogen triiodide to give you nitrogen gas, iodine. It happens very, very rapidly, and you get this supersonic bang. So that's the sort of thing that happens in an airbag, and hopefully doesn't happen to my compounds. Now I want to briefly talk to you about chemistry and polymers, and I want to tell you a little bit about this particular polymer. This molecule is called acrylic acid, and if we join these molecules together, we get a polymer. And this is an example: polyacrylic acid. This is a very useful polymer because it's a super absorbent, and this young child is not very good at bladder control, and so this is an excellent way of actually absorbing the moisture, and the young child stays dry. Polymers are, of course, everywhere. So this is a picture of a young Paul Murray who had stitches in his head. And you now put polylactide stitches in, and these over a period of about 10 days or so, these biodegrade, and you don't have to go back to the hospital to have your stitches out. And of course, we're perhaps familiar with things like polythene for packaging, plastic bags, polyvinyl chloride for waterproof plastics, and polypropylene for road markings on really quite extreme environments such as the Forth Road Bridge. Just want to very briefly touch on polymers and self-clotting bandages. We have a very talented professor at Edinburgh who's been using polymers in a number of innovative ways. What he's done is he's combined these two molecules to make something called a copolymer. And this copolymer encourages aggregation of blood platelets. And of course, that's an important role for in clotting. And so we've got self-clotting bandages potentially. Now, if we want to control the properties of polymers, then we can do that very easily as chemists. I'm going to show you this example here. This is called vinyl alcohol. That's the monomer, and if we join vinyl alcohol together, we get something called polyvinyl alcohol chains. And for this, I would need a couple of volunteers, please. I think I've got a couple of volunteers who already put in the audience. You going to come out? One. Up you come. you want to put those on? Oh. Are we going to have 3, are we? Excellent. Do you want to put those on? Do we have any more glasses? Oh, I don't think we do. Never mind. You can provide the commentary then. Would you like to hold that? And I need my other thing. I need. Okay, right. So this is my polyvinyl alcohol. I'm going to pour some of this out, and you'll see just how easy it is to pour. Right, it's very easy to pour liquid. Can you see? Could you like to stir it for me, please? Is it easy to stir? Yeah. Very easy to stir. Let's see let's see what happens if we add some of this. Keep stirring. Now what's happened? What's happened to it? It's got really thick and very, very, very hard. That's right. Okay, let's give this to your colleague then. There we go. And what you can do is you can touch it and see what it feels like. Tell me what it feels like. What does it feel like? Disgusting. Yeah. It is disgusting. It is indeed disgusting. Thank you very much. Right, so a round of applause, I think, for our volunteers. Thank you very much. And you can take this away at the end. It's something that I don't particularly want to keep because it is so disgusting. And what we've done there is we had these long chain molecules, very easy to transport over each other, a bit like snakes or noodles. But if we cross-link them with this unit here, it's much harder to move the molecules around, and we get this much more rigid material. And this is a classic example of what we do in polymer chemistry if we want to make things more rigid, higher melting, or more rigid. Now, my final demonstration then is on superconducting materials. What do we mean by a superconductor? It's something that's got below a critical temperature. It's got no electrical resistance. And the beauty about this is it means that we can pass very, very large currents through it, and we can generate very, very high magnetic fields. And sort of applications include this magnetic resonance image scanner, where we have very, very high magnetic fields, which mean we can get images from people's brains. Another property of superconductors, though, is magnetic levitation. And let's see whether we can show the magnetic levitation. So I've got in here a superconductor. I'm going to cool it with liquid nitrogen. So it's not a superconductor until I cool it. And I've got to cool it to about minus 200 degrees Celsius. And it will take a little while for that to cool. So while I'm talking about that, one of the applications of this is in magnetic levitation, which you see on the screen there for this train in Japan. What happens is that the train contains a superconductor which is cooled. It runs on a magnetic rail, and we have no contact between the train and the rail, so we reduce the friction. So if I now try and put this magnet on here, nothing's happening yet, but the magnet just sits there because we're not yet in the superconducting state. We've still got to cool this down a little bit longer. But at some point, we should reach the superconducting state. And what should happen is that the magnet will float above the superconductor. Trouble with these superconductors is they're not very good conductors of heat. So it takes quite a long time for the whole of the superconductor to actually cool down. But I think we're probably just about there now. Let's do this without freezing my fingers. Ooh. And there, hopefully, it was worth the wait, because we can show that there are indeed no strings attached there. Right. And this will happily float there as long as that superconductor remains cool below its superconducting temperature. And if you want to come and see that at the end, then please do so. I think it's a very, very important demonstration, and it's something that everybody should see and experience. So, just final slides then. Chemistry is for all, so it's for young people. It's also for older people. The average age here was 75. This is up in the Highlands. And I want some messages to give you some messages to take away for politicians and policymakers. 2 messages. One is that do please support and encourage scientific education of the young people. It's crucial. Please do support chemical research. Its impact can be huge, and I hope I've shown you some of the impact that chemistry can make. If you're a teacher or an educator, please be inspirational. Share your enthusiasm for chemistry with your students. The most important message, though, I think, is for the young people in the audience, because you are actually the future of a world which faces many, many challenges, and you can make a difference. So please do that. And all of us, let's just celebrate this International Year of Chemistry together. Let's show what chemistry can achieve. And I'm going to finish with one final demonstration, but I just want a brief advert for another International Year of Chemistry event, which is happening next Monday. It's a piece of music which has been composed by a composer, and it's celebrating chemistry. So I've got one more demonstration to finish off with. If I can remember where I put the other bottle. There it is. So we'll just finish off with a bang, because that's what chemists do. So, and this time you can watch. Oops, I've got this thread of that. You can watch the listen for the delay in this case. I've lost all my materials now. What have I done with them? Ah, there it is. There we go. So again, we have our palladium carbon. This is a slightly different mix, so we may get hopefully get a different delay. So again, this may be loud. Everybody ready? 1, 2, 3, walk away. So, thank you all very much for your attention.
Thank you, Colin. Thank you for a wonderful lecture, which your prolonged applause showed that you enjoyed it as much as I did. Colin and I, when we started doing many of these lectures, said that the 3 things we wanted to do all began with E. We wanted to enthuse, we wanted to entertain, and we wanted to educate. And Colin, you've shown it is indeed possible to do that to a wide variety, an audience that ranges from young to not so young. And everybody has sat here, and thank you very much for that lecture. And if anybody wishes afterwards to come and speak to Colin about it, then you're very welcome to do so. But before we do that, I would like to ask Tamdiel to come forward, please, and give his prize and his cheque. Our cheque, really. To Colin. Thank you very much indeed, Tam.
Colin, you are. You ask that people be inspirational on chemistry. Well, your lecture has provided an excellent example. It was inspirational. Colin, for 40 years, I had a great deal to do with Port Edgar and the Queensferry complex. Sorry to hear that you fell off the boat, but we can take comfort that chemistry came to your rescue. There were so many fascinating insights. 20 years ago, I think it was true that there was an absence of public education in science. But things have changed, and they've changed partly because of the activities of the Royal Society of Chemistry and many other bodies. And it's just not true that in this country there is an absence of drive for education in science. Colin, you have played your part, and it is with huge pleasure that I present this prize.
Thank you. Thank you for that. Very kind. Very kind of you.
This production is copyright The University of Edinburgh.